A thunderstorm over Philadelphia, June 1752. Rain needles the streets. Clouds tower, swollen and dark. Somewhere on the edge of the city, a printer turned natural philosopher stands in an open field with his young son. Benjamin Franklin holds a simple kite, its hemp string running down to a metal key and then, crucially, to a dry silk ribbon he grips inside a shelter. As the storm builds, the wet hemp string becomes conductive. Electrical charge from the storm cloud flows along it. Franklin watches the loose threads of the silk ribbon. When they suddenly stand on end, he knows the string is charged. He moves his knuckle toward the metal key. A spark jumps, small, sharp, unmistakable. It is not the dramatic, lethal lightning bolt of later legend. Franklin is not trying to call down a direct strike. That would almost certainly have killed him. Instead, he is drawing charge from the electrified air and the cloud's field, confirming an idea he had already argued on paper. Lightning and the electric fire produced in laboratories are the same phenomenon. Across the Atlantic, the same idea had just been tested with more formal apparatus. On May 10, 1752, near Paris, Thomas Francois Dalibard, following Franklin's published proposal, erected a tall iron rod grounded to the earth. During a storm, sparks leapt from the rod to a nearby conductor, showing that atmospheric electricity could be captured without a kite at all. Between the kite and the rod, something profound had happened. Electricity, long a parlor curiosity, was becoming a natural force that could be measured, compared, and even harnessed for safety. Electricity was not new to the 18th century. People had known for millennia that amber, when rubbed, could attract light objects. Indeed, the Greek word for amber, elektron, gives us electricity. But for most of history, these effects were small, fleeting, and mysterious. In the 17th century, English physician William Gilbert distinguished between electric and magnetic phenomena and argued that Earth itself was a giant magnet. In the early 18th century, experimenters like Stephen Gray discovered that some materials could conduct electrical effects over distance, while others insulated them. Charles Francois de Cisterny du Fay proposed that there were two kinds of electricity, vitreous and resinous, which attracted and repelled each other. Still, demonstrations were largely spectacular party tricks: sparks from glass tubes, crackling sounds, hair standing on end. Then, around 1745 to 1746, an accident in Europe changed everything. In Pomerania, Ewald George von Kleist discovered that holding a partly water-filled glass bottle connected to an electrostatic machine could store a strong electrical charge. Almost simultaneously, at the University of Leyden, Peter van Maschenbroek and his student Andreas Cuneus found this same effect. Cuneus famously reported receiving such a violent shock from the device that he thought he would not survive. The Leyden Jar, a glass bottle, metal foil on the inside and outside, with a conducting rod to the inner surface, had been born. For the first time, experimenters could store substantial quantities of electrical charge and release it at will. Chains of people holding hands could all be shocked at once. Multiple jars in parallel, batteries of jars, a term Franklin himself would popularize, could deliver formidable discharges. Electricity had gained a memory, a way to persist between the instant of generation and the moment of use. Into this buzzing world stepped Franklin. Living in a colonial city far from Europe's famed academies, he corresponded widely, read voraciously, and set up his own apparatus. Through systematic experiments, he proposed a theory he called the one-fluid model of electricity. Instead of phase two fluids, Franklin suggested that bodies had a normal amount of electric fluid. If they had more, they were positively charged. If they had less, negatively charged. The terminology of positive and negative charge, still used today, comes directly from his work. Franklin also clarified and popularized the distinction between conductors, metals, moist materials, and insulators, glass, silk, dry air. Articulated an early version of charge conservation, The idea that the total quantity of electric fluid in an isolated system remains constant, only moving from place to place. But his most consequential invention grew directly from his insight about lightning, the lightning rod. If lightning was electrical discharge, then it might be guided. Franklin proposed placing pointed metal rods atop buildings, connected by conductors to the ground, to draw electrical charge safely away before it built to the point of a destructive strike, or to offer a low-resistance path for any strike that did occur. The idea was controversial. Some clergy argued that intercepting lightning interfered with divine will. Early rods were blamed for unrelated fires and storms. Yet as rods protected churches, barns, ships, and public buildings, skepticism slowly gave way to acceptance. Across Europe and North America, spires sprouted metal tips. The sky's terror was being turned into a manageable risk. Electricity had left the drawing room and entered public safety. By the late 18th century, experimenters could generate static electricity, store it in Leyden jars, and draw it from storm clouds. But all of this was intermittent. Brief discharges, single sparks, episodic shocks. What if there were a way to produce a continuous electrical effect? In Bologna in the 1780s, physician and anatomist Luigi Galvani was investigating nerve and muscle function in frogs. In his laboratory, metal hooks held dissected frog legs on iron railings while static machines crackled nearby. One day, accounts differ on the exact circumstances. Galvani noticed that when a metal scalpel touched the exposed nerve of a frog's leg at the same moment that another piece of metal connected it to a different conductor, the leg twitched, even without an external spark. He interpreted these movements as evidence of animal electricity, an inherent electrical force generated by the animal's tissues, discharged when nerves and muscles were connected. Galvani's experiments, widely reproduced and refined, launched a new field that contemporaries called galvanism. The idea that the body itself might be electrical fascinated and unsettled Europeans. It later inspired cultural works like Mary Shelley's Frankenstein, 1818, where reanimation is linked to electrical forces. But not everyone agreed with Galvani's interpretation. In Lombardy, the Italian physicist Alessandro Volta saw Galvani's results differently. Volta did not deny that electricity could affect nerves, but he argued that the source of the effect was not an innate animal electricity, but the contact between different metals bridged by a moist conductor. To be continued.